review of last lecture quickly. So last lecture was vocabulary. We talked about spatial dimensionality. We talked that our flows can vary in 3 different spatial directions, which makes them 1D, 2D, or 3D. We talked about how that should stay steady doesn't change with time, and unsteady changes with time. I wonder if I can annotate this. Okay, sorry. Yeah, so that should say steady here should say steady doesn't change with time, and unsteady flows do change with time. Yeah, here we go. I got a pen. Laminar flows are generally smooth with little mixing. Turbulent flows are chaotic. There's lots of fluctuations in turbulent flows, and there's lots of mixing. And most practical flows in mechanical engineering are turbulent flows. We talked about the Eulerian perspective, which is where we watch a fixed point in space, and the Lagrangian perspective, which is where we follow the fluid as it moves throughout space. And you'll get a better understanding of those 2 different perspectives later on in the course, particularly in the module that we're starting today, which is Module 2. So Module 2 is about forces in fluid motion. So today's lecture is going to be about pressure, and then we're going to go into hydrostatics for roughly a week. So that's going to be a few lectures. These are all different, basically, forces that we have to account for in F equals ma for a fluid. So surface tension and viscosity, frictional effects. Those frictional effects produce things like boundary layers. So we'll spend a lecture talking about what boundary layers are. We also need to give special attention to the A in F equals ma, which is what this lecture is about. So that's the material derivative. I mentioned that last lecture when I was talking about uh, what allows us to relate the Eulerian and Lagrangian perspectives together. So that's the material derivative. We'll spend 1 lecture on volumetric strains. So that's kind of like how we do conservation of mass for a fluid. And then we'll put it all together and talk about Newton's second law for a fluid. But today we're just talking about pressure and the force that pressure creates within our fluid. So I'm going to list those various forces. I'm just going to give you a quick overview of F equals ma for a fluid today. We're going to understand the atomic scale or molecular scale effects. What happens on the molecular scale to cause a macroscopic effect of pressure that we feel. We'll talk about absolute and gauge pressure, which are 2 units or references that we use for pressure. So for example, when someone says the barometric pressure today is 101.325 kilopascals, we'll learn if that's absolute or gauge pressure. We're also going to do a little bit of analysis on a fluid element today and talk about the differential pressure force on a very small element of our fluid. So that's going to be our first F in F equals ma. As I mentioned, today's lecture actually begins Module 2, and Module 2 is called Forces in Fluids. Hopefully this isn't a new equation to anyone here. So summation of forces equals mass times acceleration. This is a vector equation. So if it's a 3D flow, we have 3 separate equations in this. So the little arrows indicate that this is a vector equation. So the F's in F equals ma that we're going to talk about in this course are gravity, pressure, friction, and surface tension. That's what we're going to talk about in Fluids 1. The A in F equals ma comes from the material derivative. So you're looking at Module 2. You're looking at basically the next, I want to say up till a week before the midterm. This is all what we're going to talk about. So this is a very big chunk of the course. And there's a lot of really interesting stuff you're going to learn about in this module. So I think you're going to be quite excited. So today's lecture, as I mentioned, is on pressure. So pressure produces a force that is normal to a surface. So on a molecular scale, say we have some wall here. On a molecular scale, we know that molecules are always moving. They're colliding with each other. So these molecules are moving with a certain amount of kinetic energy. They're flying around, colliding into each other. If you put a surface within that, the molecules will bump into the surface. So it's the effect of the macroscopic effect we feel is sort of a constant. But at this scale, there's, I don't know how many, say thousands happening every second that produce that macroscopic effect of pressure. So pressure produces a normal excuse me, a normal force on a surface. This force is caused by molecules colliding with a surface. So that force is caused by molecules colliding with a surface, and it produces a force through a change in momentum. So it's like an impulse. So some important properties about the pressure force are that it's always normal to a surface. So if that black line is our surface, then the pressure force is going to be normal to that surface. Sorry, I just got water. Another important property of pressure is that we can only create basically compression with this mechanism. So there's no way to create tension from pressure. So you can only press on a surface. You can't pull on a surface with pressure. You can have a relatively negative pressure, but it's basically just a lack of compression, if that makes sense. So pressure acts in compression. As I mentioned, it acts normal to any plane. So normal to a plane in a fluid. The pressure, you remember, is a scalar field. So it's defined at pressure is defined at any point in our fluid. So it's a scalar field. So what happens if I just pick some random point? The pressure actually acts in all directions. So that's at a point. So acts in all directions at a point in a fluid. So pressure is defined as the force over area. So pressure has units of pascals, or in imperial units, it could be PSI, which is pounds per square inch. So for example, pounds per square inch, pounds is a force, per square inch is an area, pascals, Newton per meter squared. So in this common definition of P equals F over A, we have some plane in our fluid here. Pressure acts normal to that. So in this is our sort of the pressure on this plane is P, and the area of this plane is A. That produces the force F here. And force is a vector, right? So it has direction. So the direction of the force is given by the normal vector of that plane. We know pressure acts normal to any surface, so you can get the direction from the normal vector of the surface. I'm going to do an example now. Okay, so this example is motivated from actually a fairly serious incident that you might have heard of that door blowing off of the airplane, the Alaska Airlines flight. So we're gonna do some calculations now on sort of the forces that door was experiencing, and this is just motivated by that, but I just picked some kind of rough numbers to get a sense of the forces that pressure can actually produce. So the example is going to be calculate the net pressure force experienced by an aircraft emergency exit door. At 16,000 feet. We're gonna, just for the simplification here, assume that door was flat. So assume the door is flat with an area of 0.6 meters squared. I'll draw the picture now. So the hull of the aircraft is kind of curved like that. We're going to assume we have kind of a flat emergency exit door here. So this is inside the plane. That's the outside air. So there's a pressure inside the plane. There's an atmosphere in there that people can breathe. So there's going to be a pressure force exerted on this door from the inside of the plane. As well, the outside air, just the normal atmosphere, that will exert a pressure force. So this door is kind of experiencing compression from both sides due to this pressure. So if the inside air pressure is different than the outside air pressure, we get a net force produced on the door, which is the case for most of flight, right? So yeah, I'm not sure if this is common knowledge. So the pressure inside an airplane is usually pressurized. It's not at sea level pressure. It's usually pressurized to a pressure of, I think, what did I use for this? I'm gonna say 8,000 feet. So anything above 8,000 feet, the air density and the pressure starts, atmospheric pressure starts going down. So the plane is basically bulging. You can think of the net forces on the plane would be creating like if the plane is a shell, it creates like a tension. So the plane is being pulled like that. So I will give you those pressures now. So inside that pressure for 8,000, I think this is 8,000 feet, but I'll just give you the atmospheric pressure there. So 75.3 kilopascals. And sea level pressure is like 100, roughly 100 kilopascals. So the pressure that they normally keep the planes at is a little bit below sea level pressure. That's part of the reason that people kind of tend to swell on airplanes, because the pressure is lower. Our body pressure there would be higher than it. The body pressure relative to the atmosphere is higher than it normally is at 8,000 feet. So that's why I think that's one of the reasons that people bulge. So this is yeah, people well, I shouldn't say bulge. People tend to swell. So you have like those compression socks, stuff like that. So the outside air pressure is 55 kilopascals at that altitude. So that's at 16,000 feet. I'll calculate these two forces here. So I'll draw the forces on this door. The forces in this case, if we assume our door is kind of a straight rectangle, like just a plain rectangle, the forces would act directly on the center of that door. So the force from the pressure inside the plane is pressure inside the plane times the door's area. So that's 75.3. So kilopascals is 10 to the 3 pascals times 0.6 meters squared. So pascals is units of newtons per meter squared. Multiply that by area meter squared and we get 45 kilonewtons, which is quite a large force. The force on the outside, again, is the pressure area outside. So that will be 55 kilopascals. So that's 33 kilonewtons. So that 45 kilonewtons from the inside, the way I've drawn the diagram would be to the right. This one would be pointing to the left. So as I mentioned, it's the difference between these pressures that creates a net force on the door. If they were balanced, the door wouldn't experience a net force. The pressures would equal out. So for example, when they pressurize the plane when it's on the ground, if they pressurize it to the if they pressurize the plane when it's on the ground, when they seal it to 8,000 feet pressure, it would actually be the net pressure would be pushing the plane because the atmospheric pressure on the ground is higher. Okay, so anyways, the difference between these is 12 kilonewtons. So that is I still like to think of things in pounds, so that's roughly almost 3,000 pounds. So that's like the weight of a small car. So the door, this is again, these are all just kind of like a back of the napkin, back of the envelope calculations. But the force on that door is like the weight of a small car. So you can see if you have some loose bolts or things aren't attached correctly, the decompression happens very fast. So that door gets blown off very fast. So that's some of the forces that the plane normally has to deal with. So even when you're on a plane normally, and they normally fly higher than 16,000 feet, the forces will be even higher, say on that emergency exit door. So any questions on this example? Oh, it was pretty straightforward forces. So now we're going to talk about pressure definitions. So in this case, I used atmospheric pressure of say 75 kilopascals, and I've been saying sea level pressure is say 100 kilopascals. So what does that mean? And in engineering, like when you go fill up your tires and you say you fill them to like 30 psi, what does that mean? So important pressure definitions. So all pressures, when you say it, you can, during this, it might help you to draw analogy to the way we talk about temperatures. So you know that when you say a certain temperature in degrees Celsius, you're giving it to reference to the Celsius scale. And the Celsius scale is defined at 0 for freezing point of water and 100 for boiling point of water. It's the same thing with pressure. You know, like in Celsius, you can also equivalently give the same temperature in units of Kelvin, and Kelvin is referenced to absolute zero. So it's very similar for pressure. So we can reference to absolute, which is complete vacuum, basically no molecules at all, or we can reference to gauge, which is relative to atmosphere. So all pressures are stated relative to a reference pressure. So whenever someone tells you pressure, they're implicitly, they may not know it, but they're stating it relative to a reference. Just like when people say it's, minus, I don't know, whatever it is out there right now, like minus a million degrees, they're stating relative to a reference. So if that reference is the atmospheric pressure, then the pressure we give is called gauge pressure. Gauge pressure is the most common type of pressure we deal with in engineering. The other case is if reference is absolute vacuum, then we call it absolute pressure. I'm going to draw a little schematic here just to clarify this. So say we have let's say this is a reference. So this is P equals 0. Let me just redraw this. P equals 0. So that would be absolute 0 or absolute vacuum. So that's a complete vacuum. It's actually quite hard to get to this vacuum. Even in space, you usually have some molecules. So that absolute vacuum is pure P equals 0. So that's the absolute lowest pressure that one could ever get to. So above this absolute vacuum, we define atmospheric pressure. So that atmospheric pressure is, of course, positive. So you never hear someone say like the atmospheric pressure today is like -2 kilopascals. It's always positive. So atmospheric pressure is usually given as absolute pressure. So relative to absolute 0. Would be like if, yeah, I don't think there's a good analogy with temperature there. But atmospheric pressure is in absolute pressure units. So the gauge pressure is defined relative to atmospheric pressure. So that would be, say, P sub G. So if we're above atmospheric pressure, it's positive. And if we're below atmospheric pressure, it's negative. Are there any questions about gauge pressure? Yes.
My understanding is that when you're having gauge pressure, it's the pressure of whatever you're measuring compared to its surroundings. But like the pressure in this room might not be the exact same as like what we typically think of as atmospheric pressure.
That's true. Yeah.
So, but it would still be gauge pressure, right? If I were to just
Yeah.
like take the reference of like a canister to this room.
Yeah, it's one of the most confusing parts about gauge pressure. The reason I'll explain a little bit more about why we define gauge pressure like that. But the reason is, say you're to pressurize something in this room, it doesn't have to compete with the atmospheric pressure at sea level. It has to compete with the pressure in this room. So that's why we use gauge pressure. So if we want to be clear, we sometimes tack on an extra letter to the units of pressure to indicate whether it's gauge or absolute. So if we want to be clear, we sometimes use units of, say, kilopascals gauge or kilopascals absolute. So if you come across a unit like, for example, PSI-G, that means PSI gauge or PSI absolute. So in some safety critical applications, it's important to state, because sometimes the pressures get so high. Normally you can tell like a gauge pressure of say you inflate your, yeah, the gauge pressure is normally like small relative to the atmospheric pressure because atmospheric pressure is quite high. So a lot of the times you can just tell like a say 15 psi, that's probably not going to be an absolute pressure. But the gauge, the G and the A really help. So I'll try and use those when I'm having you guys do, just so you get used to them, uh, because it's more precise that way when you specify the unit. This is like our degree C or degree or Kelvin. So this is mostly context dependent. So gauge pressure can be positive or negative. So if gauge pressure is positive, then it's usually called positive pressure. If it's negative, that means that it's usually referred to as vacuum. So I have some pictures now I can show. And the reason that it is, as you guess, called gauge pressure is it's relative to, so say you have some sort of equipment here, and there's a pressure gauge. That looks like pressures in units of bar on that gauge. Some other things here. Again, another pressure gauge. So that looks like it's in bar. You can see, actually, if I make this bigger, you can see the pressure on this actually goes to negative. So that kind of tells you it's a gauge pressure because you can't have negative absolute pressure. And it would be very annoying to go and recalibrate all of your pressure gauges for absolute pressure because you would have to, pressure gauge usually measures the difference between, just implicitly, it measures the difference between absolute and the pressure of whatever we're measuring. So if you wanted a absolute pressure gauge, you would need to recalibrate it every time the pressure in the room changes. And another example I mentioned was filling up the car tires. So for example, one time I had a flat tire. This was actually during my undergrad. I had a flat tire and my friend was helping me fill in my tire. And you start out, like my tire was really flat. So it only had a few like PSI of pressure in there. Even say it was zero, say it was completely flat. The pressure in your tire is zero. It's not at absolute vacuum. It's just at zero, meaning that it's the same as the local atmospheric pressure. So your pressure gauge will say zero. But you're not you haven't achieved like an absolute vacuum in your car tire. I'll be a little bit more clear about how this could actually affect things that we're designing in engineering. So we have some sort of pressure vessel here. Say we have this pressure vessel and we say our gauge pressure is positive. The net forces, for example, like that gauge pressure being positive was what the airplane emergency exit door example had. So the net forces on this pressure vessel would be like this. So they want to cause this pressure vessel to expand. That actually tends to produce a bit of a stiffening effect on this pressure vessel. So it's good for structure. But if the gauge pressure is below zero, the net forces are like this. So the net force distribution on this would be sort of causing this to buckle or collapse. And the difference between these two cases are so important that there's actually totally different codes that govern whether or not the vessel operates under positive or negative pressure. The design guidelines are much more stringent if you have a vacuum vessel. So in some cases, the chemical engineers say we need that to be at a vacuum pressure. So we have to basically, as mechanical engineers, figure out how to design things under vacuum. So the difference is the structural, like I said, there's a stiffening effect, but it can actually get quite complicated. So it's important to distinguish whether or not pressure equipment operates at a positive or negative pressure. Any questions about that example? Okay, so let's do some math. Now we're going to compute the force due to pressure on a fluid element. I'm actually going to replace element with parcel here just to, sorry about that, just so we're using the same language. Remember, parcel is a differential element of our fluid. Okay, so let's draw a fluid element here. So we're going to say our fluid parcel is kind of a cube. We'll define our coordinate system like this. So the cube has length in the x direction dx, which is very small. It's a fluid parcel, so very small. Length in the z direction is dz, and the height is dy. So then we can compute the area of all these different, so the top area is dx dz. Side area is dy dz. Its frontal area is dx dy. I'm going to consider, which one am I going to consider here? I'm going to consider looking down the z-axis at this surface here. So we're going to analyze in detail this surface, and then we'll see how that extends to. Consider this one surface of the cube. So this is one surface. So at the top we have, you might remember we have, since we have the kind of that top face of this cube. So there's going to be a pressure applied there, which is going to create a force. Same thing at the bottom and the left and right sides of the cube. So so I'm absolutely clear, this box is kind of this face. So the pressure here, the pressure force there is actually coming from the pressure acting on the right side of the cube. And same thing with the left side of the cube and the top. So what is that force actually? Let's say we have let's define the pressure at that face as P1. So the force there is P1 dy dz. Force on the right hand side, so we're doing the x direction forces, is P1 plus partial P by partial x times dx. So that's the pressure on that face. And the area of that face is dy dz. So I'll explain that partial p partial x dx term. So partial p partial x gives us the rate of change of pressure as we move in the x direction. So if we multiply that rate of change by the amount that we moved in the x direction, then we get the new pressure value. So partial p partial x is the rate of change there, and then we move dx. Remember the length of this is dx. So then now we get the new pressure at dx away from the left face. Okay, I'll do the same thing on the top and bottom. So on the top and bottom, I'll say the bottom is P2 dx dz. Top one will be P2 plus partial P partial y, and we moved up dy times the area there, which is dx dz. Any questions about that? Are you guys comfortable with this partial p partial x dx thing? So. I can keep explaining it a bunch of different ways, but if you guys are good with it. So maybe just a show of hands. Who's okay with this? Medium? Okay. So say you have some sort of, say you have a point here and you want to compute the value here. Say you have some sort of axis like this. You know the distance between these 2 points is, say, a, and if you assume that it's going to be a linear variation, say you know the slope here. Actually, we're trying to compute basically wherever. So we don't actually know the value of our variable we're trying to find in the right. But we know, if you know the slope and you know the distance, you can compute that value. So the slope in this case, I say this is x. So the slope is dy dx. So the value here, this value is, say this is y1, this is y2. So y2 is dy dx times a. That's the change plus y1. So that's all we're doing when we move from the left face to the right face. Yes, please.
A question that I can't really intuit. So how can we add it to one side but we don't take it away?
How can we add it to one side but we don't take it away from the other side? Because of where we've defined P1. So if we say P1 is in the middle, then you're right, we would have to do partial P partial x dx over 2 because we would move. Say we say P1 is there, then the pressure on this face would be P1 minus partial P partial x dx over 2 because we move half dx. So we say P1 is the pressure here. To get here, we basically just do this. Does this make sense now? Makes more sense? Okay. So that's one face of our cube. And this allows us to do the balance in, well, the x direction. So we have, remember our force is a vector. So let's define some sort of differential force vector. So this df is the differential force created on this differential element by pressure. So it's just a force, but we say df because it acts on our dx, dy, dz differential cube. So df is dfx I hat plus dfy j hat plus dfz k hat. That's our differential force vector. We can compute this differential force vector now because we've computed the pressure forces on those faces of our cube. So dfx is going to basically just be the sum of forces in the x direction on this cube. And I've drawn all the forces we have in the x direction on this diagram here. So that would be P1 dy, P1 dy dz. The force on the other face is negative. Remember, pressure always acts normal to the face. In fact, it always compresses the face. So that's why I've drawn all the arrows compressing this cube. So minus P1 plus partial P partial x dx dy dz. So again, all of these things in the diagram are just F is PA. And I find P using the partial P partial x, say, or partial P partial y. And I find A just from the geometry of this cube. So that's our dfx. Interesting thing here is that the P1s actually cancel. So that's negative partial P by partial x dx dy dz. Have I lost anyone with the force summation there? Just the x direction forces? I'm just adding these two arrows together. So this one minus this one. That's all that is. Okay? Same thing in the y direction. dfy is p2 dx dz minus so we kind of get a trend here. I didn't draw the z direction forces, but we would get, I'll just leave those details out because you can see clearly now. It's negative partial p by partial z dx dy dz. So now we can assemble our differential force vector. So it's negative partial p by partial x I hat minus partial p by partial y j hat minus partial p by partial z k hat. All of that times dx dy dz. And you've actually seen this, what this is before in your calculus class. So the df, and I'll add a sub p here just to indicate this is the force due to pressure only. That's what we're talking about today, the force due to pressure. So dfp is negative nabla p, which is the gradient of p dv, where v is basically length, width, height, right? So that's dx dy dz. So this tells us that, I'll just wait to catch up before you guys. So this tells us that the net force due to pressure on a small element of our fluid is related to the difference in pressure at that point. So the gradient of pressure, so the gradient operator, just a quick review, the gradient of a scalar produces a vector. So the x component is the partial and partial p partial x, the y component is partial p partial y, the z component is partial p partial z. So it's the gradient of pressure that produces a force in our fluid. And this makes sense. Just the same way that the gradient of temperature produces heat transfer, So the gradient of pressure, it doesn't matter how high the pressure is here. It matters if the pressure is different over here. If there's a gradient, that's going to create the force. So that's what pressure gradient is and how it produces this force in our fluid. The reason that it's negative is similar to in heat transfer. So say we have some region of our flow. This region has a high pressure. This region has a low pressure. So the gradient will be here. The gradient tells us the direction of change. But if you have like a high pressure and a low pressure, you know the force kind of intuitively is going to be the opposite direction. So the high pressure is going to push on the low pressure. So this will be FP. I'll say DF. I'll just say FP. So that's the reason for the negative sign. That's the intuitive reason, but it came actually directly out of our analysis on a differential element. Are there any questions about this? Just review what we did today. So today we talked about F equals ma. We just derived one of the forces in F equals ma. It's related to the pressure gradient. That's what produces the force. It's not pressure itself, it's the pressure gradient. We talked about, pressure comes from these molecular collisions. It acts normal to a plane in a fluid, normal to a surface, but it acts in all directions at a single point. The reason that it acts normal to the plane is, say it acts all directions at all the points on that plane, they'll cancel out. Anything along the plane will cancel out so that things only act normal to the plane. We calculated like using just F equals PA, so the net force on, say, an emergency exit door, just to see how much force can be produced by pressure. We talked about absolute and gauge pressures, and that most of the time gauge pressure is what we're using in engineering when we're defining pressure. For example, these pressure gauges, they go negative to positive because gauge pressure just tells us where we are relative to the atmosphere. Same thing with pressure equipment here. We derived that the force due to pressure on a differential fluid element, all it is at the end of the day, the force due to pressure on a differential element is just the gradient of pressure at that fluid element times the volume of that fluid element. I should say the negative gradient of pressure. So if there's high, low pressure, we know the force will actually be from, like the flow will go from high pressure to low pressure, just the same way heat transfer goes from high to low. So that's the reason for the negative, because the gradient is actually points from low to high. Are there any questions before I wrap up? Okay. Yeah, just a reminder for your tutorial tomorrow, and thanks everyone that's on for today.